Everyone. So in this video, we're going to talk about an optimization application and kind of what sort of makes an optimization application different from a related rates application. So the first thing is that we need to know kind of some key terminology that tells us that it's an optimization problem. So for example, if we look at this problem here, we know that Natalia is swimming in a shallow lake 75 feet offshore and 200 feet away from a snack bar, and she suddenly realizes she's hungry, wants to get lunch as quickly as possible. So if Natalia can move 2 feet per second through the water and 8 feet per second on shore, where should Natalia swim in order to minimize the time it takes her to reach the snack bar? So the key word here really is minimize. Like, that's the word that tells me that I need to optimize something. I'm trying to find either a maximum or a minimum. Maybe it's maximizing profit, maybe it's minimizing time or costs or something like that. But that word minimize is what tells me that it's an optimization problem. Okay, so before we kind of go through it, let's talk about the process there. So the first thing we always have to do in an optimization application is draw a diagram and organize our information. So in this case here, the diagram is kind of given to us, but let's make sure we understand where everything comes from. So the 75 is the 75 feet offshore. She's 200 feet away from the snack bar along the shoreline here. Y is going to represent the distance she travels through the water, and X is going to represent the distance down the shoreline that she leaves the water and enters land. And then this 200 minus X, what that's going to be is the distance she travels on land. So she's traveling Y feet over through the water and 200 minus X feet through land. The next thing we have to do is identify any constraints. So that's kind of what we just talked about a little bit. I know that for one, I know that x squared plus 75 squared has to equal y squared, so that would technically be a constraint. And I know that the distance is going to be this y times 200 minus x. All right. It's not like some of the problems we've done where we have a limited amount of material to work with or anything like that, or we have to have a certain volume. This is kind of more constrained by the distances in this case. The next thing we need to do is we need to figure out, well, what's the equation that we're trying to optimize? So in this case here, I should always know that distance is equal to rate times time, or in other words, time is equal to distance over the rate. All right, so that means that the time it's going to take Natalia to reach the snack bar is going to be the distance she traveled through the water, which is y, over the speed through the water, the rate through the water, which is 2, plus the distance over the land, which is 200 minus x, divided by the rate over the land, which was 8. Okay, so that's going to kind of be the key function here in this problem. This is the one that I'm going to have to work with throughout the problem in order to minimize it. And then the last step is to differentiate that equation to find either the maximum or the minimum. In this case, obviously, we're looking for the minimum. All right, so let's create a little bit of space for ourselves here so we can go through this. And we know that t is going to equal y over 2 plus 200 minus x over 8. So I'm just going to kind of simplify that out a little bit. So I have different terms here. And so let me just get a different color here. So we have t is equal to y over 2 plus 200 over 8, which could actually be simplified even further, not necessary now, minus x over 8. All right, and what I'm going to do is I really want to have t in terms of x, and right now I have t in terms of y and x. I would want one variable so it's easier to take the derivative and to work with it there. So remember, the other thing we know is that x squared plus 75 squared was going to equal y squared. In other words, y is equal to the square root of 75 squared, which is 5,625, plus x squared. And so what we're going to do is we're going to take that value of y and we're going to plug it back into this original problem we had up here. So now we have t is equal to the square root of 5625 plus x squared, all of that is over 2, plus 200 over 8 minus x over 8. All right, and then this is the function that we're going to have to find the derivative of. We want to minimize that. So if we go to find t prime, that derivative here, all right, we can imagine it being raised to the 1/2 power, and then we're going to have to use chain rule for that what's inside right there. But we're going to get 1/2 times 1 over 2 times the square root of 5625 plus x squared times the derivative of what's inside, which was 2x, and then plus the derivative of 200 over 8, which is 0, and then the derivative right here is just going to be minus 1/8. And if we kind of clean that up a little bit, we're going to get t prime is equal to, let's see, the 1/2 and the 2 would cancel. That's going to give me an x over 2 times the square root, 5625 plus x squared minus 1/8. All right. So what we're going to do now is take our derivative, and we have to set it equal to 0 in order to minimize it. So I'm going to take this equation here for t prime, make sure that it equals 0, and go ahead and find the solution for t. So first thing I'm going to do is add the 1/8 to the other side. So now I have x over 2 times the square root, 5625 plus x squared is equal to 1/8. And if we cross multiply that, we're going to get simply that 8x is equal to 2 times this whole square root. And we're going to divide both sides by 2 and then square it. So 4x, right? If I divide by 2, this is going to be 4. And if I square both sides, I should get 16x squared is equal to 5,625 plus x squared. Subtract x squared from both sides, we get 15x squared. It's 5625. Divide by 15, x squared is going to equal 375. And then if I take that square root, I should get that x is equal to, you could simplify it, I think it's going to come out to be about 5 root 19, which is roughly 19.365. Okay, so what that actually means, let's put our unit in here, feet. So what that actually means is that Natalia, in order to minimize time, should leave the water or enter the shore 19.365 feet down shore. In other words, she should swim so that this distance here is 19.365 feet. Okay. I hope this helps. I'm going to try and upload a couple other optimization related rates videos as well.